have Professor Paul Simon Kench, who is from the Department of Geography. Professor Kench's research focuses on environmental change and climatic variability. And in particular, he is interested in how climate change and sea level change affects the evolution and dynamics of coral reef islands. He has made significant contributions to global discussions on the future adaptation options for small island nations, including providing kind of a keen advisory role. It's very fascinating, but he also mentions in his bio that he has presented much of his work at the UN General Assembly in 2018. So we're very happy to have him tell us more about his work on the response of coral reef islands to sea level rise. Professor Kench.
Thank you very much, and good afternoon, everybody. I'll just try and share my screen right now, so you can see my presentation, and hopefully everyone is seeing that.
Yeah, it looks great.
Thanks. As part of my introduction, I was introduced as someone who works on kind of physical landscapes, and I belong to the Department of Geography, which is a fascinating department in the sense that it draws or has people in it that work on things as diverse as the physical environment, like I do, right through to the human and social dimensions of the environment and cities, and provides a really fertile ground to kind of explore the interactions between physical and social and human processes. With that, I'm a professor of tropical coastal change, and have spent a considerable part of my career investigating how coastal landforms evolve and how they change over time. And of course, with the prospect of sea level rise and accelerated sea level rise in the recent past and over the next century, this has provided me with a really nice rationale for my work and trying to consider how the coast changes and what does this mean for coastal communities. So my example today really draws on 15 or 20 years of research work that I've been involved with and led, which explores specifically the problem of coral reef islands and their susceptibility to sea level change. And of course, they're lovely places to work. So one advantage of being a physical geographer and being able to roam around the planet, going to wonderful places. Where I'd like to, just before we move on, just explain what I'll be talking about in the next quarter of an hour or so. And I'm going to focus on the most remote islands in the Indian and Pacific Oceans. And these are part of what are called low-lying atoll nations. And I'm going to focus on the Marshall Islands here in the Central Pacific, Kiribati, Tuvalu, Tokelau, and indeed the Maldives in the Central Indian Ocean. And by no means is the work we presented just limited to those places, because coral reef islands are throughout Southeast Asia as well. And indeed, that is a future focus of my work. But I'm going to be focusing on the work that I've done in particularly the Southwest Pacific. And here's a blow-up image of the Southwest Pacific on these atoll chains. And each of the triangles you see is an individual coral atoll, and I'll show you what those look like in a moment, arranged in these rather curious ridges or lines through the central Pacific Ocean. And I'm going to spend a lot of time today talking about Tuvalu, which is, I guess, one of the smallest nations on the planet, but also has held a very prominent position in climate change discussions about its susceptibility to climate change and indeed whether it will exist into the future. So what do these places look like? On the top left photo here, you see a typical atoll, which is really a near circular or annular coral reef that's grown from the ocean depths. And that coral reef encircles a lagoon. And these features can be several kilometers to 100 kilometers in diameter. And on the very edge of this atoll, you'll see this green color. And these are actually the islands. And if we sort of fly down onto the island surface, they look something like these other panels here. And there's a few things I want you to note about these islands before we proceed. The first is that they're all small and they're all generally low-lying, less than 2 or 3 meters above current sea level. The other thing is to note is that what they're made of is really the broken up remains of corals, shells, and other organisms that grow on the coral reef. And as waves break up those organisms, they really transport and dump really the skeletal remains of these organisms and piles on the reef, which later become vegetated and form the substrate upon which people can live. These islands are also quite small. So here we're looking at the atoll rim in Tarawa and Kiribati. And this island is probably only 800 meters in width, but might extend for some 10 kilometers along shore. And we also find islands in the settings on the right-hand side, which are individual islands sitting on its own little coral reef platform and can range in size from 0.5 kilometre to maybe 2 kilometres, and which support human habitation. And because they're low-lying and sea level is going up, they're considered to be physically very sensitive to changes in sea level change and the wave climate. The other intriguing part of these islands, of course, is that they are host to human populations, and quite dense populations. And this is the capital city of Male in the Maldives, which is only 1 square kilometre in area, but has more than 140,000 people living on it. So not only are these intriguing physical environmental systems, they're also incredibly complicated and fascinating human systems. And if you just start to think about how a city like this functions in terms of the water, the energy, the resources required to keep this urban centre going, it is quite remarkable. And of course, if sea level starts to go up, we are commonly told that these islands will start to erode. And one of the main pieces of evidence we are shown is sort of falling trees or coconuts along the shoreline, evidence of shoreline retreat. And we're also told that these islands will become flooded and simply drown as sea level rises. And here's a shot of the urban area of Funafuti Atoll in Tuvalu. The bottom panel is actually the shoreline of that island Male, and you can start to put together that if sea level does increase, what the threats are to the urban infrastructure in a system like Male. And in some ways, it's the same concerns that the Singapore government share with accelerated sea level rise, and what are its options for adaptation in the future. So as a consequence of these islands being low in elevation, quite remote, and sea level is going up, the common discourse in popular science and media outlets is that small island nations are under threat. Indeed, headlines such as this suggest they will disappear from our ocean systems over the next 50 to 100 years, or at least be uninhabitable in the next 2 to 3 decades. And when I began my work in this area, what struck me was assertions and statements such as this was seldom based on actually any empirical data whatsoever about how the islands formed and how they behave, but rather was based on a simple assumption that an island must be a relatively static feature, and if sea level goes up, would simply drown these island systems. So that's really been the spur for my research program for the last 15 or 20 years. And we started this by simply saying, well, how have islands changed in that time frame, and what evidence have we got to say that these islands are disappearing as sea level increases? So we started this work in Tuvalu, and here is a map from the Southwest Pacific, and what it shows is rates of sea level change. And what I'd like you to note is this sort of white hot sort of tongue that travels west-east across the western part of the Pacific is an area that shows that sea level has risen 2 to 3 times faster in this part of the Pacific Ocean than elsewhere globally. And that is a zone where Tuvalu is situated. And we thought, okay, sea level has been rising for a considerable period of time in this part of the Pacific. What have the islands done? And how did we go about that? As we drew on some robust and traditional geographic analysis tools. And in Tuvalu, we were very fortunate that we've had some very early geological maps of the islands that were made in the main atoll of Funafuti. And of course, these were, as it says on this panel, developed in the late 1800s. And subsequent to that, of course, as the advent of aircraft and photography developed, we have suites of aerial photographs that have taken pictures of the islands. And more commonly now, we have a suite of satellites that are continually whirring around our planet, taking images of landforms almost on a daily, if not hourly basis. And so we spent a lot of time collating these older and newer data sets to allow us to compare how these islands have changed on their reef surfaces over the time frame in which we know sea level has started to increase. And I'm going to share with you some of the primary results of this work in very summary form. We started our work just looking at one atoll, this small atoll you can see here of Funafuti in Tuvalu, which contains some 28, 29 islands. What we found, and this in a subsequent study across the entire archipelago, is that the land area in Tuvalu has increased by 7% over the last century. What we also found is that every single island we looked at had changed. It's altered its position on its reef surface. And all the change isn't the same. We had 18 islands that increased in area. And the example you can see on the right-hand panel, what we're looking at in the green dashed line is the outline of these islands in 1897. And the blue line represents the outline of this island in 2010. And you can see that it's essentially welded together and become one larger island on the reef surface. And the islands increased in area from small amounts up to 6.5 hectares over that time frame. And while that doesn't seem a lot in area, it's a substantial land addition in the context of these small islands. Of course, we also had some islands that decreased in area. And again, this green dashed line represents 1896, and the blue line represents 2010, with the black aerial photo being about 1972. So this island actually decreased in area by some 23%. But on balance, the amount of land in this atoll had increased by 7%. What this work also enabled us to do is figure out how these islands are actually changing on the reef surface. And we noticed that a number of islands appeared to be rotating on the spot, if you like, on their reefs. Other islands seem to be coalescing and fusing together on the reef surface. And still further islands were starting to migrate away from the ocean towards the lagoon. So it was a very powerful tool for us to start thinking about, how the islands are changing and how the islands are beginning to change. But of course, when we published this data, it was quite a small data set of close to 30 islands in a sea of tens of thousands of islands. And we've spent the last decade trying to build up this data set so it is more robust. And what I'm going to show you next is a summary of more than 1,000 very similar analyses that you've just seen of islands. So every data point you see on this graph represents analysis of old photos and satellite images of how an island has changed. And what you're looking at on the horizontal axis is the size of an island. And on the vertical axis is the percentage of change in these islands. And we have some changes that have increased more than 200% in island area over a 50 or 60 year time frame, and some changes where islands have contracted in size. But when we analyse this data set, what we establish was that close to 80% of these islands have either grown in size or at least remain exactly the same size as they were 50 or 60 years ago. And we have a much smaller subset, close to about 22%, which have decreased in size on the reef surface. And I just want to explore this a little bit more with you using that same data. If we look at the left-hand side of this panel, these are the smallest islands, less than 5 hectares, so quite tiny. And what we noticed is that the behaviour of those islands was hugely variable. And indeed, we had 3 islands that totally disappeared over that time frame of analysis. And here's one example from Sorel 7 in the Federated States of Micronesia, a close to 3 hectare island in 1944, which had largely been devegetated and wasn't really a subaerial or an island above sea level by 2014. But the more common response that we saw in these small islands was enormous variability in its behaviour. Some had contracted substantially, some had got quite a lot larger in size, and some had started to move around on its reef surface very quickly or very rapidly. So they were the small islands. And if we go to the other side of this diagram, what we can see is that these are more stable. And these are our largest islands, more than 10 hectares in size. And these are the islands that people quite sensibly have chosen to live on in the past. And what we found in this collection of islands is considerable stability and expansion of island area. And here's one example that shows reasonably stable in its position, but grown by 5 hectares over a time frame of 60 years or so. And I'm going to show you one more example of this category. It's an island in Kiribati, the island of Abemama, or one of the islands in Abemama. And what I want you to see here is that the red line is 1945 outline of this island, and you see the 2018 satellite image. And I think there's a couple of remarkable things about this. One is there's been 3 hectares of accretion or expansion of this island, but also a substantive amount of change. And if you look closely at the lagoon shoreline, it has started to be used for village development. So people have started to occupy this newly accreted land. So what does all this mean? Well, over 15 years or so, I've had multiple PhD and master students work on this kind of data. What we can conclude is that despite sea level going up by quite substantial amounts, islands appear to have persisted on these coral reef surfaces, and that land area has actually increased in most of the atoll systems examined. Doesn't mean all islands have expanded. Some have got smaller, but many have got larger, and on a net aggregate, there's been more land available in these atoll systems. And perhaps the thing that we like to press home most strongly is that the islands are very dynamic and are continually moving, adjusting on their reef surfaces. So that's kind of one major piece of the work that we began, and we published that, and it's slightly counterintuitive, and that's where it starts to enter the political dimension of small island nations not particularly liking this message because it doesn't send a message of vulnerability and doom and gloom, which is a very powerful message for them on the international stage when it comes to climate change negotiations. Some of the critique around this work that we've received was that, well, we've only really mapped islands moving in the horizontal plane. We're looking at planform change, but if sea level is going to go up, they're still going to drown, regardless of whether they're moving around. And so we've been working for the last 5 to 10 years on that vertical dimension to see whether these islands do have the capability to increase their land level along with sea level change. And I'm only going to show you 3 slides to sort of summarize some of this work and where we think it's leading. But I want you to take this shot in and start thinking about it. This is a drone image of an atoll reef rim in the Maldives. And what I want you to note is that these reefs are a filter to incident ocean swell. So the ocean waves ride in and interact with the edge of the reef, which is the white water you see in the foreground. And then the water drains and runs across the reef flat surface and interacts with the island shoreline, which you see in the upper part of the image. Now, I want you to think about what conditions exist that might allow the waves to increase in elevation or get larger and be able to travel across the reef surface and interact with the island. And what I'm going to show in this little pop-up, if I can get it working, is one example of an extreme wave event that interacted with the islands in the Maldives and washed straight up and over these islands and indeed kept on going. And this is the 2004 tsunami that was generated off Banda Aceh, which travelled across the Indian Ocean. And it's one example of how waves can get up and over the islands, but there are multiple other ways: cyclones or typhoons, major storm events, and indeed something called long period swell events, where waves travel up from the Southern Ocean and impact the reefs and islands, can cause similar inundation episodes. And from my perspective on how do islands form and change, we started to ponder, what does this do to an island? And again, I'm going back to satellite imagery here. This is an island in the Federated States of Micronesia. The panel, this one, which shows the more green image, was taken prior to a major cyclone event. And this image here, the paler one, was taken about a month after the cyclone event. And you'll notice some substantial changes, and these are the sorts of changes we can begin to map and detect from remote sensing analysis. And I guess the question is, what is all that white material and where does it come from and what's it doing to the island surface? And these, what we call wave overwash events, are a mechanism that allow material from the reef and the beaches to be transported onto the island surface and enable them to increase in elevation. And it's called overwash deposition, which provides new layers of island building material to the island surface. If we fly down onto an island such as that one and have a look at what it means when we're in the field, you see these lovely fresh white sand sheets that have been pushed up and over the edge of the island and onto the island surface as a result of this wave overtopping or wave overwashing. And these are new additions of sediment to the island surface that can be up to 20 or 30 centimetres thick. On this right-hand panel, we started to dig holes through the island to see what it looked like, and we can start to unravel the paleohistory of how this island has formed. And I'll just take a few moments to explain what you're looking at in this right-hand image. This dark line here, just at the top of the ruler, was the island surface immediately prior to the Indian Ocean tsunami. The tsunami came along and deposited this 15 to 20 centimetres of fresh sediment on the island surface. Waves all receded, and this grey line represents the development of a leaf litter layer and a new soil developing on the island. 3 years later, there was another wave inundation event from the Southern Ocean that added this new layer of material to the island surface. And if you look way down the bottom of this hole, you'll see a layer there that's a little bit more mottled, but is probably an even earlier wave overtopping episode. And so we think we now have plenty of evidence to suggest that as our islands are moving around on their reef surface, these episodic wave inundation processes provide a mechanism that also allow these islands to increase in elevation in a vertical sense. And we have a number of examples in the Maldives, for example, where these islands have kept pace with sea level in terms of their rate of vertical building. So in conclusion, it's a body of work that I've been working on for 20 years, had probably 70 or 80 publications around this kind of work. But what are we distilling from this is that these islands are hugely changeable, or in our parlance, dynamic. And the threat is not that islands are going to be drowning as sea level goes up, is that they're changing and moving. And from our view, that is an equally big challenge for island communities and countries to deal with. They are continually adjusting. They are increasing in size, which is a positive dimension to the work that we've done, and they can build vertically. But you can start to imagine, well, how do you deal with that? If you're planning a new adaptation future in these small island nations, how do you do it so that these islands can coexist with the dynamism and the changes that are taking place? And we believe, and we've got some evidence for this, is that the changes we're observing are likely to get more rapid as a consequence of sea level going up over the next 50 to 100 years as well. So as I said, the challenge is really, how do island communities coexist with this? Which brings me back to a final statement about the power of geography. I'm a physical scientist working in this space, trying to understand how the islands change and what this means for communities. And I now have colleagues at universities around the world who are interested in how we use these results and work with communities to think, how does this impact the community? How can they possibly respond to this? And it's a hugely challenging subject, and it's going to be hugely challenging for governments. But I guess the positive note in our work is that there is time. We can't sit on our hands for 20 or 30 years, but there is time over the next decade to hold robust discussions about a more resilient future for these small islands that reflect the natural dynamism and probably build on traditional mechanisms that island communities used to adopt, and how they coexist with these changing landscapes about them. And I'll leave it there. Thank you very much.